Tonight, I'm going to show you something that will break your brain. Not because it's complicated, but because your mind literally cannot process it. The universe is big. You already know that. But here's what you don't know. Every single mental picture you've ever had of the universe, every image, every analogy, every classroom model, every documentary you've ever watched, all of them are wrong. Not slightly wrong, catastrophically wrong. The real universe is so much larger than what you're imagining right now that the gap between your picture and reality is itself larger than anything you've ever conceived. And the most unsettling part, even after I explain it, even after you hear every number and every comparison tonight, your brain still won't fully grasp it. It physically can't. And I'm going to show you why. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it means a huge difference for me. Now, let's begin. Let's start with something you already understand: distance. You deal with distance every single day of your life. You know how far it is from your bed to your kitchen. You know how long it takes to walk to the end of your street. You know that the grocery store is maybe a mile or two away, and that your workplace might be a 20-minute drive across town. These are distances that make sense to you. They fit inside your head. You can picture them. You can feel them in your legs and in the time they take. If someone tells you a coffee shop is half a mile away, you know what that means. You've walked half a mile before. It takes maybe 8 or 9 minutes at a comfortable pace. You'll pass some houses, maybe a few trees, cross a street or two, and you're there. The distance is real in a way you can experience directly. Your brain handles this effortlessly because it was designed for exactly this kind of calculation. And I mean designed quite literally. Human beings evolved on the plains of East Africa over hundreds of thousands of years. Our ancestors needed to judge distances constantly. How far away is that predator? How far to the nearest water source? Can I throw this rock far enough to hit that animal? Can I make it back to camp before nightfall? These were life and death calculations, and the humans who were better at making them survived and passed on their genes. The ones who misjudged distances, who thought the lion was farther away than it actually was, or who underestimated how far they'd need to walk before finding water, they didn't make it. Natural selection fine-tuned our brains over thousands of generations to be extremely good at judging distances from a few feet to maybe a few miles. That's the range that mattered for survival. That's the range our brains are optimized for. And for most of human history, that range was all we needed. The farthest most people ever traveled was maybe a few hundred miles in their entire lifetime. A journey of 1,000 miles was the kind of thing legends were made of. The idea that the Earth was round and that you could theoretically keep walking in one direction and end up back where you started was so counterintuitive that it took centuries for the idea to be widely accepted. The circumference of Earth at the equator is about 25,000 miles. That's a number you can write down and say out loud. 25,000 miles. You might even nod when you hear it because you've heard it before. But can you really picture it? Can you feel it? Think about the longest trip you've ever taken. Maybe you drove across a country or flew across an ocean. Now multiply that by whatever factor is necessary to get to 25,000 miles. Your brain can do the math, but it can't do the feeling. You can calculate it, but you can't experience it intuitively. And 25,000 miles is just the circumference of one planet, one small rocky planet orbiting one ordinary star. We haven't even left home yet, and already your intuition is starting to strain. Now, let's take a small step outward. The moon, our closest celestial neighbor. The moon orbits Earth at an average distance of about 239,000 miles. It's not a distance you've ever traveled unless you happen to be friends with one of the very few humans who flew to the moon during the Apollo program. When the Apollo astronauts made that journey, they traveled in a spacecraft moving at roughly 25,000 miles per hour, and it still took them about 3 days to get there. 3 full days of hurtling through empty space at a speed that would let you circle the entire Earth in 1 hour. And after 3 days at that speed, you'd arrive at the moon, the closest thing to us in all of space. Here's something most people don't appreciate about the Earth-Moon distance. If you took every other planet in the solar system, Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune, and you line them up side by side, they would all fit in the gap between the Earth and the Moon with room to spare. That's how much empty space exists between us and our nearest neighbor. When you see illustrations or models of the Earth and Moon, they're almost always shown too close together. The real distance is enormous relative to the sizes of the objects. If Earth were the size of a basketball, the Moon would be a tennis ball sitting about 23 feet away. Most people would guess maybe a foot or two. That's how badly our intuition fails even at this very first step into space. But the Moon is practically sitting in our lap compared to what comes next. The Sun is about 93 million miles from Earth. 93 million. Let's try to unpack that. If you could drive to the Sun at highway speed, say 60 miles per hour, without stopping for gas or food or sleep, it would take you about 177 years. Not days, not months, years. Nearly 2 full centuries of continuous driving. You would be long dead before you arrived. Your children would be dead. Your grandchildren would be dead. The car you started driving would have rusted to nothing and been replaced dozens of times. And you still wouldn't be there. Light covers this distance in about 8 minutes and 20 seconds. Light, which travels at approximately 186,000 miles per second, the fastest speed anything in the universe can achieve, needs over 8 minutes to reach us from the Sun. This means that when you look at the Sun, you're not seeing it as it is right now. You're seeing it as it was 8 minutes ago. If the Sun suddenly vanished this very instant, you would continue to see it shining in the sky for another 8 minutes and 20 seconds. You'd feel its warmth. You'd see its light. Everything would seem perfectly normal. And then 8 minutes later, the sky would go dark. Not because the Sun disappeared in that moment, but because it disappeared 8 minutes earlier and the information, traveling at the fastest possible speed, only just reached you. This is your first real clue that something is profoundly different about cosmic distances. They're so large that even light, the fastest thing that exists, the absolute speed limit of the universe, needs measurable time to cross them. And we're still inside our own solar system. We haven't gone anywhere yet. Let's keep going. Mars, depending on where it is in its orbit relative to Earth, can be anywhere from about 34 million miles to 250 million miles away. When NASA sends rovers to Mars, commands from mission control travel at the speed of light, but they still take between 3 and 22 minutes to arrive, depending on the orbital geometry. You can't drive a Mars rover in real time. The delay is too long. If the rover is about to drive off a cliff, by the time that image reaches Earth and engineers send a stop command, over 6 minutes could pass, minimum. The rover has to be smart enough to handle problems on its own because help is literally minutes away, even at the speed of light. Jupiter is about 484 million miles from the Sun on average. Saturn is about 891 million miles out. When the Cassini spacecraft orbited Saturn, every photograph it took traveled back to Earth as a radio signal at the speed of light. And that signal took over an hour to arrive. An hour. At the speed of light. These are still planets in our own solar system. Neptune, the most distant planet, orbits at about 2,800,000,000 miles from the Sun. Light from the Sun takes over 4 hours to reach Neptune. The Voyager 2 spacecraft, which flew past Neptune in 1989, was so far away that its radio signals, traveling at light speed, took over 4 hours to reach Earth. And that was a spacecraft we launched in the late 1970s that had been flying for 12 years at that point. Now, Voyager 1, which launched the same year, has been traveling through space for nearly 5 decades. It's the most distant human-made object in existence. As of now, it's roughly 15 billion miles from Earth. That's a staggering distance by any human measure. Light takes about 22.5 hours to travel from Voyager 1 to Earth. It's so far away that a round-trip communication takes nearly 2 full days. And yet, Voyager 1 has barely left the solar system. It crossed the heliopause, the boundary where the sun's influence fades into interstellar space, back in 2012. But in terms of reaching the next star, it hasn't even started. If Voyager 1 were aimed at Proxima Centauri, the closest star to our Sun, at its current speed of about 38,000 miles per hour, it would take approximately 73,000 years to get there. 73,000 years, let that register. All of recorded human history spans roughly 5,000 years. Writing was invented about 5,000 years ago. The pyramids were built about 4,600 years ago. Everything that humans have ever written down, every empire that has risen and fallen, every war, every discovery, every love story, every tragedy, all of it fits inside 5,000 years. Voyager would need to travel for more than 14 times that entire span of history to reach the nearest star. And it's already moving incredibly fast by human standards. This is where most people's sense of scale completely collapses. And this is the point I need you to understand before we go any further. Your brain was not built for this. And I don't mean that as a figure of speech. I mean it as a neurological fact. The human brain processes spatial information using mental models that are rooted in personal experience. You understand a mile because you've walked one. You understand 100 miles because you have driven one. You can stretch your imagination to 1,000 miles, 10,000 miles, maybe even the circumference of the Earth. But beyond that, the numbers become abstract. They're just numbers. They stop connecting to anything real in your experience. You can hear me say 93 million miles to the sun, and you can write it down, and you can do math with it, but you cannot feel it. You cannot picture it the way you can picture the walk to your kitchen. The mental machinery required to truly grasp 93 million miles simply doesn't exist in the human brain because evolution never needed to build it. And here's the problem. 93 million miles is nothing. It's the distance to our own star. It's essentially zero on the scale of the universe. Everything I've described so far, the moon, the sun, the planets, Voyager 1 drifting through interstellar space, all of it is contained within a region so small that it would be invisible on a map of just our galaxy, let alone the universe. We haven't even started talking about real cosmic distances yet, and already, your intuition has failed completely. Let me try an analogy that might help. Imagine you're standing on the shore of an ocean, right at the water's edge. The wet sand under your feet represents everything we've talked about so far. The moon, the sun, all the planets, the Kuiper Belt, Voyager 1, the entire solar system. All of it fits in the wet sand under your feet. The ocean stretching out in front of you, going all the way to the horizon and far beyond it, that's the rest of the universe. You haven't even gotten your ankles wet yet. That's how far we've come in our journey tonight. We've covered the wet sand, and we think we've gone somewhere. We haven't. The ocean hasn't even begun. This is what I mean when I say the universe is much bigger than you think. It's not that you think the universe is small. You already know it's big. Everyone knows the universe is big. That's common knowledge. But knowing it's big and understanding how big are completely different things. Knowing is intellectual, understanding is experiential, and the gap between the two when it comes to the universe is itself larger than anything you've ever imagined. Let's talk about light years for a moment, because this is the unit astronomers use to measure distances beyond our solar system, and understanding it properly is crucial. A light year is the distance that light travels in 1 year. Light moves at about 186,000 miles per second. In 1 year, moving at that speed continuously, light covers about 5.88 trillion miles. That is 1 light year. Now, that number is so large that it's effectively meaningless to the human mind. Your brain sees the word trillion and files it under very big number alongside billion and million, treating them all as roughly equivalent. But they're not equivalent. They're separated by factors of 1,000. 1,000,000 seconds is about 11.5 days. 1,000,000,000 seconds is about 32 years. 1,000,000,000,000 seconds is about 32,000 years. The difference between 1,000,000 and 1,000,000,000,000 is the difference between a week and a half and 32 millennia. And a light year is almost 6 trillion miles. 6 trillion individual miles, each one the distance you might drive in a few minutes on a highway, laid end to end, stretching across the emptiness of space for a distance so vast that it takes light itself, the fastest thing in the universe, an entire year to cross it. And here's the key. A light year is just the starting unit. It's the base measurement astronomers use because anything smaller is too small to be useful. Using miles or kilometers to measure distances between stars would be like using inches to measure the distance between continents. You could do it, but the numbers would be so absurdly large that they would communicate nothing. Light years are the smallest practical unit for stellar distances, and even light years produce numbers that challenge comprehension once you start looking at the larger universe. But let's not jump ahead. Let's stay with light for a moment, because understanding the speed of light and what it means is essential to grasping why the universe is so much bigger than you think. The speed of light isn't just fast. It's the speed limit of the universe. Nothing can exceed it. This isn't an engineering limitation. It's not that we haven't built rockets fast enough yet. It's a fundamental law of physics, woven into the fabric of space-time itself. Albert Einstein showed in 1905 that as an object with mass accelerates toward the speed of light, its energy requirement increases without limit. To actually reach the speed of light, you would need infinite energy, and infinite energy doesn't exist. So nothing with mass can ever travel at light speed. Only massless particles like photons, the particles that make up light itself, travel at light speed. And they must always travel at exactly that speed. They can't slow down. They can't speed up. From the instant they're created to the instant they're absorbed, they move at 186,000 miles per second. No faster, no slower, ever. This has been confirmed by over a century of experiments. It's not theoretical, it's observed, measured, tested, and proven. Particle accelerators routinely push subatomic particles to 99.999% of light speed. And even at these extreme velocities, they cannot reach 100%. The energy required increases asymptotically. You get closer and closer, but you never arrive. This means that light speed is not just a speed, it's a wall. A hard, absolute physical wall that nothing in the universe can cross. And this wall has consequences that most people don't fully appreciate. Because if light is the fastest thing possible, and if even light needs years to travel between stars, then those distances represent real, physical barriers, not barriers that better technology will eventually overcome. Barriers built into the structure of reality itself. When we say the nearest star is about 4 light years away, we're saying that even traveling at the maximum possible speed in the universe, it would take more than 4 years to get there. And no spacecraft we've ever built has come anywhere close to light speed. The Parker Solar Probe, the fastest spacecraft in history, reaches speeds of about 120 miles per second at its peak. That's astonishingly fast. That's fast enough to travel from New York to Los Angeles in about 20 seconds. But it's still only about 0.065% of the speed of light. At the Parker Solar Probe's top speed, reaching Proxima Centauri would take about 6,800 years. And that's the nearest star, just the closest one. Most stars are much, much farther away. The distances escalate so rapidly from here that even light years start to feel inadequate. But we're not there yet. We've established something critical in this opening stretch. Human intuition has a ceiling. That ceiling exists because our brains evolved to handle distances measured in feet, in miles, maybe in hundreds of miles. Cosmic distances don't just exceed that ceiling. They shatter it so completely that the pieces can't even be found. Every analogy we use, every comparison, every mental model is an attempt to translate something fundamentally untranslatable into terms we can sort of almost vaguely understand. And even the best translations fail, because the universe isn't just big. It's big in a way that the word big was never designed to describe. Think about it this way. You have a mental picture of the solar system in your head right now. Maybe it looks like a classroom model with the sun at the center and the planets arranged neatly around it. That picture, whatever it looks like, is wrong. Not because the planets are in the wrong order, but because the scale is wrong. In every classroom model, in every textbook illustration, the planets are shown far too close to the sun and far too close to each other. Real space is almost entirely empty. If you made a scale model of the solar system where the sun was the size of a bowling ball, Earth would be a tiny grain of sand about 86 feet away. Jupiter would be a marble about 450 feet away. Neptune would be a slightly smaller marble over half a mile away. And the nearest star, Proxima Centauri, would be another bowling ball sitting about 4,500 miles away. You'd need to place it roughly in Hawaii if your model sun was in New York. And there would be absolutely nothing in between. No stars, no planets, nothing. Just mile after mile after mile of empty space. That emptiness is something your brain resists. We're pattern-seeking creatures. We look for objects, landmarks, structure. We don't intuitively understand vast emptiness. When you look up at the night sky and see stars scattered across the darkness, your brain interprets them as being reasonably close together, like lights on a ceiling. But they're not. Each of those stars is separated from its nearest neighbor by trillions of miles of nothing. The night sky is a profound illusion. It looks full, but it's almost entirely empty. The stars are so far apart that the space between them dwarfs the stars themselves by factors of millions. This is the fundamental problem with understanding the universe. It's not just that the numbers are big, it's that the numbers are so much bigger than the numbers you're used to, that the normal mental tools for handling big numbers don't work. Going from your daily experience to cosmic scales isn't like going from a pond to an ocean. It's like going from a pond to something so vast that every ocean on Earth would be a single water molecule inside it. The jump in scale is not linear. It's not even exponential in any way your intuition can track. It's a category shift. You're not dealing with bigger versions of familiar distances anymore. You're dealing with a completely different kind of distance, one that your brain has no framework for processing. And that's just within our solar system and the nearby stars. We haven't talked about the galaxy yet. We haven't talked about other galaxies. We haven't talked about galaxy clusters, or superclusters, or the cosmic web, or the observable universe, or what might lie beyond it. Every single one of those steps involves another massive jump in scale. Another moment where the previous distance, which already seemed impossibly large, suddenly becomes trivially small. That's what's coming. That's the journey ahead. And I want you to hold on to this feeling right now. This feeling of your intuition straining at the edges, because that feeling is about to get much, much more intense. Everything you've heard so far tonight has been the introduction. The distances we've covered, Earth to the moon, Earth to the sun, across the solar system, out to Voyager, they're the warm-up. The real scale of the universe hasn't even entered the picture yet. And when it does, these distances, these numbers that already feel impossibly large, are going to shrink to nothing. Not to something small, to nothing. To a rounding error so insignificant it wouldn't even show up on a graph. Because the universe is much bigger than you think. And as the title says, it's not even close. Now we leave home. Everything we talked about so far, the moon, the sun, the planets, Voyager drifting through the darkness, all of that was our front porch. We've been standing at the door of our house, looking at our own yard, and marveling at how big it seemed. But now we step off the porch and into the neighborhood. And the neighborhood is where things start to become genuinely disturbing. The nearest star to our sun is Proxima Centauri. It's part of the Alpha Centauri system, which is actually a triple star system. two larger stars, Alpha Centauri A and Alpha Centauri B, orbit each other, and Proxima Centauri, a small red dwarf, orbits both of them at a great distance. Proxima Centauri is about 4.24 light years away. You've probably heard that number before. 4.24 light years. It sounds almost manageable, doesn't it? 4.25, that's less than 5. 5 is a small number. You can count to 5 on one hand. How far could it really be? Let's find out. 4.24 light years is roughly 25 trillion miles. 25 trillion. That's a 25 followed by 12 zeros. To make this number mean something, let's try several different approaches because no single comparison is going to be enough. If you could somehow board a commercial airplane and fly directly to Proxima Centauri at a cruising speed of about 550 miles per hour, your flight would last approximately 5 million years. 5 million years on an airplane. Modern humans have only existed for about 300,000 years. So you would need to have boarded that plane roughly 17 times further back in time than our entire species has existed. You'd have been flying since long before anything resembling a human walked the earth. The first hominids were just beginning to diverge from other apes 5 million years ago. You'd board the plane as a pre-human ancestor and arrive as whatever humans have evolved into 5 million years from now, assuming you somehow survived the journey. If you drove a car at 70 miles per hour, non-stop, 24 hours a day, 7 days a week, with no breaks, no fuel stops, no rest, just constant forward motion, it would take you about 40 million years to reach Proxima Centauri. 40 million years. The dinosaurs went extinct 66 million years ago. You'd have needed to start driving when there were still large dinosaur-like creatures roaming the Earth. And you'd arrive in a future so distant that the continents would have drifted into unrecognizable positions. Even with the fastest spacecraft humanity has ever built, the Parker Solar Probe at its peak speed of roughly 120 miles per second. Reaching Proxima Centauri would take about 6,800 years. That's longer than all of recorded human history. The Sumerians were inventing writing about 5,000 years ago. You could have launched this mission before the first word was ever written down, and it still wouldn't have arrived yet. You'd still have nearly 2,000 years of waiting left. Now, here's the analogy I want you to carry with you through the rest of this journey. Imagine you shrink the sun down to the size of a grain of sand. A single grain of sand, tiny enough to sit on your fingertip. At that scale, the Earth would be a microscopic speck, orbiting about an inch away, far too small to see with the naked eye. The entire solar system, all 8 planets, the Kuiper Belt, everything, would fit within a circle maybe 50 feet across. Now, where would Proxima Centauri be? Another grain of sand sitting about 4.5 miles away. 4.5 miles of absolutely nothing. No stars, no planets, no light, no matter. Just empty space. Mile after mile of pure void, with a grain of sand at each end. That's the distance to the nearest star. That's the closest thing to us in interstellar space. And here's the detail that really twists the knife. Proxima Centauri is unusually close. It's the nearest star to our sun. Most stars are much farther away. The stellar neighborhood within about 20 light years of Earth contains only about 130 known star systems. Beyond that, the density of stars doesn't increase dramatically. Stars in our region of the galaxy are typically separated by 4 to 5 light years on average, each one isolated in its own vast bubble of emptiness. The galaxy isn't a crowded room full of stars. It's more like a desert at night where each campfire is separated from the next by miles and miles of cold, empty sand. Let's talk about some of the stars in our broader neighborhood and what their distances mean. Because this is where distance becomes time and the universe starts doing something genuinely strange. Sirius is the brightest star in the night sky. You've almost certainly seen it without knowing its name. It's a brilliant blue-white star in the constellation Canis Major, and it sits about 8.6 light-years from Earth. That means the light entering your eye when you look at Sirius tonight left that star 8.6 years ago. You're not seeing Sirius as it is right now. You're seeing it as it was nearly a decade ago. Whatever Sirius is doing at this exact moment, you won't know for another 8.5 years, because the light carrying that information hasn't reached you yet. This is one of the most important concepts in understanding cosmic distances. Distance and time are fused together. When you look out into space, you're literally looking back in time. Every object you see as it was in the past. The farther away something is, the further into the past you're looking. This isn't poetry or metaphor, it's physics. Light has a finite speed. It takes time to travel. The information it carries about distant objects is always old by the time it arrives. Vega, another bright star visible in the northern hemisphere, is about 25 light-years away. When you look at Vega tonight, you're seeing light that started its journey 25 years ago. If you're 25 years old, that light has been traveling since the day you were born. It left Vega before you took your first breath, crossed 25 light-years of interstellar space, and arrived at your retina tonight carrying an image of a star as it looked a quarter century ago. Arcturus, the brightest star in the northern celestial hemisphere, is about 37 light-years away. Its light has been traveling for nearly 4 decades. Polaris, the North Star, is about 445 light-years from Earth. The light you see from Polaris tonight began its journey around the year 1581. That was before the founding of Jamestown, before the Pilgrims landed at Plymouth Rock, before Shakespeare wrote most of his plays. That light was already years into its journey when Galileo first pointed a telescope at the sky. It's been crossing the void between Polaris and Earth for over 4 centuries, and it arrives tonight at your eye, carrying an image of a star as it appeared during the Renaissance. Betelgeuse, the famous red supergiant in the constellation Orion, is roughly 700 light-years away. Some estimates put it closer to 600, some closer to 700, but the point remains the same. The light you see from Betelgeuse left that star during the Middle Ages. Cathedrals were being built in Europe. The Mongol Empire was at its height. Entire civilizations have risen and fallen during the time it took for that light to reach you. And Betelgeuse is interesting for another reason. It's a massive, dying star that will eventually explode as a supernova. When that happens, it will briefly shine as bright as the full moon, visible even during the day. But here's the unsettling part. Betelgeuse might have already exploded. The explosion could have happened hundreds of years ago. It could have happened while Columbus was sailing to the Americas, or while Napoleon was marching across Europe. But we wouldn't know. The light from that explosion would still be traveling toward us, moving at 186,000 miles per second, and it wouldn't arrive for centuries. We would continue to see Betelgeuse sitting peacefully in Orion's shoulder, completely unaware that the star had already torn itself apart. We'd be looking at a ghost, an afterimage of something that no longer exists. This is what distance means in the universe. It doesn't just separate objects in space, it separates them in time. Every star in the night sky is a window into a different moment in history. Some are windows into last decade. Some are windows into the time of Shakespeare. Some are windows into the age of the dinosaurs. And none of them show you the present. The present, for every star except our own sun, is hidden from us behind a wall of light travel time that we can never see past. Now, everything I've described so far, Sirius, Vega, Polaris, Betelgeuse, every single one of these stars is inside our own galaxy, the Milky Way. Every star you have ever seen with your naked eye, every star that has ever appeared in any constellation used by any human civilization throughout history is a member of the Milky Way. We've never seen a single individual star in another galaxy with our unaided eyes. The Milky Way is all we see, and the Milky Way is enormous. Our galaxy is a barred spiral, a vast pinwheel of stars, gas and dust, rotating slowly in the darkness. It stretches roughly 100,000 light years from one edge to the other. 100,000 light years. Light, traveling at the maximum speed the universe allows, needs 100,000 years to cross from one side of our galaxy to the other. The last time light from the far edge of the Milky Way started a journey toward where we are now, modern humans hadn't even left Africa yet. Neanderthals were still alive. The Ice Age was in full grip. Woolly mammoths roamed the plains of Europe. That light has been traveling ever since, through all of human evolution, through the invention of agriculture, through the rise and fall of every civilization, through the invention of science itself, and it still hasn't arrived. The Milky Way contains somewhere between 100 billion and 400 billion stars. The exact number is uncertain because counting stars in a galaxy you're inside of is extraordinarily difficult. It's like standing in the middle of a vast forest and trying to count every tree, including the ones hidden behind other trees, the ones obscured by fog, and the ones so far away you can't even see them. But the best estimates place the number at roughly 200 to 300 billion. Let's settle on a number near the middle. About 250 billion stars. 250 billion. That's 250,000 million. To count to 250 billion, counting one number per second, non-stop, no sleeping, no eating, no breaks, would take you about 7,900 years. You'd need to have started counting around the time humans first began farming, and you'd finish roughly 3,000 years from now. And each of those numbers represents a star. A real, physical object. A ball of fusing hydrogen, generating light and heat. Many of them with planets orbiting around them. Our sun, the star that makes life on Earth possible, the star that feels so central and important to us, is just one of those 250 billion. There's nothing special about it from a galactic perspective. It's a G-type main sequence star, sometimes called a yellow dwarf. It's average in brightness, average in mass, average in temperature, average in age. If the galaxy were a city, the sun would be one unremarkable house in one unremarkable neighborhood, on one unremarkable street. You'd drive past it without a second glance. Our sun sits about 26,000 light years from the center of the Milky Way, roughly halfway out from the core, tucked into a minor spiral arm called the Orion Spur. We're not in the center of the galaxy. We're not even in a major spiral arm. We're in a small offshoot, a side street in the galactic suburbs. The light from the stars at the center of the Milky Way if we could see through all the dust blocking our view, started its journey 26,000 years ago. When that light began traveling, humans were still in the Stone Age. There were no permanent settlements, no agriculture, no written language. People lived in small nomadic groups, hunting and gathering, using tools made of bone and flint. Everything we call civilization, from the first farms in Mesopotamia to the smartphone you might be holding right now, all of it happened during the time it took light to travel from the galactic center to Earth. And that's not even light from the other side of the galaxy. That's light from the middle. At the very heart of the Milky Way sits something extraordinary and terrifying. A supermassive black hole called Sagittarius A star. This object has a mass of about 4 million times the mass of our Sun, all compressed into a region of space smaller than the orbit of Mercury. A black hole is a place where gravity has become so intense that nothing can escape, not matter, not radiation, not even light. The boundary beyond which nothing returns is called the event horizon, and for Sagittarius, a star, that boundary is roughly 17 times the diameter of our Sun. All that mass compressed into that relatively small space. Stars near the galactic center orbit Sagittarius, a star at tremendous speeds. One star, known as S2, completes a full orbit every 16 years, reaching velocities of about 2.5% of the speed of light at its closest approach. That's roughly 17 million miles per hour. By tracking the orbits of stars like S2 over decades, astronomers confirmed that Sagittarius A star was indeed a supermassive black hole. This work earned Reinhard Genzel and Andrea Ghez the Nobel Prize in Physics in 2020. Right now, Sagittarius A star is relatively quiet. It's not actively consuming large amounts of matter, but there's evidence that about 6 million years ago, it went through a period of intense activity, releasing enormous bubbles of energy that extend above and below the galactic plane for tens of thousands of light years. These structures, called the Fermi bubbles, are remnants of a time when the heart of our galaxy was far more violent than it is today. The region around the galactic center is dramatically different from our quiet suburban neighborhood. Stars are packed thousands of times more densely. If you lived on a planet there, your night sky would be ablaze with stars so bright that true darkness might never come. But that density comes at a cost. Supernovae would be more frequent. Radiation levels would be higher. Gravitational interactions could fling planets out of their orbits without warning. Our position in the galactic suburbs, quiet and relatively uneventful, might be one of the reasons life had the stability it needed to evolve on Earth over billions of years. The Sun orbits the center of the Milky Way, just as the Earth orbits the Sun. But while Earth takes 1 year to complete its orbit, the Sun takes about 225 million to 250 million years to go around the galaxy once. This period is sometimes called a galactic year or a cosmic year. The last time the Sun was at roughly this position in its orbit around the galaxy, dinosaurs were just beginning to appear on Earth. The time before that, complex multicellular life was still relatively new. Earth has existed for about 20 galactic years. The universe itself has existed for about 60. These timescales are so vast that they make human history seem like a camera flash in the middle of a long, long night. And during those orbits, the Sun doesn't just glide smoothly through empty space. It passes through different regions of the galaxy, Sometimes it travels through the sparse gaps between spiral arms, where stars are few and the radiation environment is calm. Other times it plunges into or near the major spiral arms themselves, where massive young stars burn hot and die fast as supernovae. Some scientists have speculated that mass extinction events on Earth might correlate with the sun's passage through denser galactic regions, where increased radiation or gravitational disturbances could have sent comets raining into the inner solar system. The evidence is debated, but the idea is remarkable. The fate of life on Earth might be connected to where our sun happens to be in its slow, quarter-billion-year lap around the galaxy. I want you to try to picture the Milky Way, but I want you to picture it honestly, not the way it appears in most illustrations. Most images of spiral galaxies show a dense, bright structure packed with stars. And while the galaxy does contain hundreds of billions of stars, it's also mostly empty space. If you randomly selected a location inside the Milky Way's disk, the chances of that location being inside a star or anywhere near a star would be astronomically small. The average distance between stars in our region of the galaxy is about 4 to 5 light years. 4 to 5 light years of empty space between each star and its nearest neighbor. In denser regions near the galactic center, stars are closer together. In the outskirts, they're farther apart. But everywhere in the galaxy, the dominant feature is emptiness. The stars are like grains of sand scattered across a beach the size of a continent. There are a lot of grains, but the beach is unimaginably bigger. Here's something that helps put the Milky Way's size in perspective. Every star you can see in the night sky with your unaided eye is within about 4,000 light years of Earth. That sounds like a lot, and it is. 4,000 light years encompasses millions of stars. But the Milky Way is 100,000 light years across. That means everything you can see, every star, every constellation, every point of light in the sky on the darkest, clearest night, is contained within a tiny bubble that represents roughly 4% of the galaxy's diameter. 96% of the Milky Way is beyond what your naked eye can detect. You see a tiny neighborhood and mistake it for the whole city. And here's something that makes these vast distances feel even more consequential. We now know that most of the stars in that galaxy have planets. This isn't speculation. It's one of the most important astronomical discoveries of the past 3 decades. Before 1992, we knew of exactly one planetary system in the entire universe. Ours. We assumed other stars probably had planets, but we had no proof. Then astronomers began detecting them. First around a pulsar, then around a normal sun-like star. The Kepler Space Telescope, launched in 2009, revolutionized our understanding by watching over 150,000 stars for the tiny dip in brightness that occurs when a planet passes in front of its star. Kepler found thousands of planets, and by analyzing how many it found versus how many it statistically should have missed, astronomers concluded something staggering. On average, every star in the Milky Way has at least one planet. Some have 5, 6, 7, or more. The galaxy doesn't just contain 250 billion stars. It contains at least as many planets, and probably far more. Among those planets, a significant fraction orbit in the habitable zone of their stars, the region where temperatures could allow liquid water to exist on a rocky surface. Estimates vary, but many astronomers believe there could be tens of billions of roughly Earth-sized rocky planets in the habitable zones of stars within the Milky Way alone. tens of billions of worlds where, in principle, conditions might allow liquid water, organic chemistry, and possibly life. Our galaxy is not just a collection of stars scattered across 100,000 light-years of space. It's a vast archipelago of worlds, tens of billions of potential harbors for the kind of chemistry that, on at least one world, led to living things. And yet, as far as we currently know, not one of those worlds has sent us a signal. Not one has shown us evidence of technology. Not one has revealed itself as anything other than a distant dot of reflected starlight. The galaxy is enormous, filled with worlds, and as far as we can tell, silent. If you were somehow transported to a location outside the Milky Way and could look back at our galaxy from a distance, the sun wouldn't be visible. Not without an extremely powerful telescope. It would be one dim point of light among hundreds of billions, lost in the glow of the spiral arms. And Earth? Earth would be completely invisible. Utterly, absolutely undetectable. A tiny rocky planet orbiting one average star among hundreds of billions. No telescope we could currently build would be able to see Earth from outside the galaxy. It would be like trying to spot a single grain of pollen clinging to one specific leaf on one specific tree in a forest that stretches across an entire continent. You wouldn't find it. You couldn't find it. The scale difference is simply too enormous. And yet, the Milky Way, this colossal structure containing hundreds of billions of stars and at least as many planets, stretching 100,000 light-years from edge to edge, harboring a supermassive black hole at its heart, so large that light itself needs 100 millennia to cross it, is not even close to the whole story. In fact, it's barely the introduction, because here's what we knew for most of human history. We thought the Milky Way was everything. Until roughly a century ago, most astronomers believed the Milky Way was the entire universe. There was nothing else. The fuzzy patches of light that people occasionally saw through telescopes were thought to be clouds of gas within our galaxy. They were called nebulae, from the Latin word for cloud, and no one suspected they were anything more. Then, in 1924, an astronomer named Edwin Hubble changed everything. Hubble was studying a fuzzy patch of light called the Andromeda Nebula, using what was then the most powerful telescope in the world, the 100-inch Hooker telescope on Mount Wilson in California. He identified individual stars within the Andromeda Nebula, specifically a type of star called a Cepheid variable. Cepheid variables are stars that pulsate in brightness with a period that's directly related to their intrinsic luminosity. If you know how bright a star actually is, and you can measure how bright it appears from Earth, you can calculate how far away it is. Using this technique, Hubble calculated that the Andromeda Nebula was roughly 900,000 light-years away. His number was actually an underestimate. The modern measurement puts it at about 2.5 million light-years. But the key point was the same either way. Andromeda was far outside the Milky Way. It wasn't a gas cloud within our galaxy. It was an entirely separate galaxy, comparable in size to our own, containing its own hundreds of billions of stars. This was one of the most profound discoveries in the history of science. In a single observation, the known universe expanded by a factor of thousands. The Milky Way went from being everything to being one galaxy among many. It was as if you'd spent your entire life thinking your house was the entire world. And then one day you opened the front door and saw a city stretching to the horizon, filled with millions of other houses just like yours. The Andromeda Galaxy is a spiral galaxy similar to the Milky Way, but larger. It contains roughly 1 trillion stars, about 2 to 4 times as many as the Milky Way. It's about 220,000 light years across, more than twice the diameter of our galaxy, and it's on a collision course with us. The two galaxies are falling toward each other at about 250,000 miles per hour. In about 4.5 billion years, they'll begin to merge, their spiral structures disrupted by gravitational interactions, eventually settling into a single large elliptical galaxy containing the combined stars of both. But Andromeda isn't the only other galaxy. Once astronomers knew what to look for, they started finding galaxies everywhere. The local group, our immediate cosmic neighborhood, contains about 50 galaxies. Most of them are small dwarf galaxies with a few billion stars or less. The Milky Way and Andromeda are the two dominant members, the gravitational anchors around which the smaller galaxies orbit. And here's where I need you to brace yourself, because the local group, with its 50 or so galaxies, is tiny. It's the smallest meaningful structure in the hierarchy of cosmic organization. Beyond the local group, there are galaxy clusters containing hundreds or thousands of galaxies. Beyond those clusters, there are superclusters containing hundreds of clusters. Beyond the superclusters, there are filaments and walls containing thousands of superclusters. And beyond those, there is the observable universe, containing roughly 2 trillion galaxies in total. 2 trillion galaxies, each one containing millions, billions, or even trillions of stars. The Milky Way, which seemed so impossibly vast just moments ago, is one galaxy out of 2 trillion. If you randomly picked a galaxy from the observable universe, the odds of picking the Milky Way would be 1 in 2 trillion. That's a probability so small, it's effectively zero. And every single one of those 2 trillion galaxies is separated from the others by millions or billions of light years of empty space. The distances within the Milky Way were already beyond comprehension. The distances between galaxies make those internal distances look trivial. Andromeda is 2.5 million light years away, and it's the closest large galaxy to us. Most galaxies are hundreds of millions or billions of light years away. The light from the most distant galaxies we've observed has been traveling for over 13 billion years. Since the universe was less than 1 billion years old, everything we've discussed about the Milky Way, the hundreds of billions of stars, the hundreds of billions of planets, the 100,000 light-year diameter, the 26,000 light-year distance to the galactic center, the supermassive black hole sitting at its heart, all of it describes one structure. One island of light in an ocean of darkness so vast that the island itself becomes invisible from any meaningful distance. The Milky Way is not the universe. It's not even a significant fraction of the universe. It's one galaxy among trillions, one structure in a cosmic web so large that describing it requires units of measurement that didn't exist a century ago. The Milky Way is your entire sky. Every star you see belongs to it. It contains every world humanity has ever known, and every world will likely visit for thousands of years to come. It's home, but it's also just the beginning. And as we zoom out further, past the local group, past galaxy clusters, past superclusters, what you're going to discover is that even the Milky Way, with all its billions of stars and its 100,000 light-year span, is barely a speck in what comes next. Your brain built a model of the universe. It put the solar system in the center, expanded outward to the nearby stars, and stretched to encompass the Milky Way. That model felt big, it felt complete, but it isn't. It captures less than a trillionth of what's actually out there. The real universe is about to walk into the room, and when it does, everything we've talked about so far is going to shrink down to a point so small it vanishes from view. And your brain, the same brain that couldn't truly grasp 93 million miles to the sun, is about to be asked to comprehend distances billions of times larger. It can't do it. You already know that, but we're going to try anyway. Because even a failed attempt at comprehension reveals something true about the cosmos, something that pure numbers alone never could. The universe doesn't care whether you can picture it. It exists at scales that make human understanding not just difficult, but nearly irrelevant. And understanding the sheer hopelessness of the task, is itself a kind of understanding. It's the honest kind. The kind that doesn't pretend. The kind that looks at the numbers and admits that something this large simply can't be held in a mind this small. And we're only getting started. Now we enter territory where the human mind starts to genuinely break down. Not struggle, not strain, break. Because we're about to leave the Milky Way behind and zoom out into a universe so vast that our entire galaxy, with its hundreds of billions of stars and its 100,000 light-year diameter, becomes a dot, then a speck, then nothing. Let's start with the local group, our immediate cosmic neighborhood. The Milky Way, Andromeda, Triangulum, and about 50 smaller galaxies are all gravitationally bound together in a region spanning roughly 10 million light years. 10 million light years, that's 100 times the diameter of the Milky Way. If the Milky Way were a dinner plate, the local group would be a space about the size of a large living room, with 2 dinner plates representing the Milky Way and Andromeda, a saucer for Triangulum, and a bunch of crumbs scattered around for the dwarf galaxies. Most of that living room would be empty. Galaxies don't fill space. They float in it, separated by vast gulfs of nothing. But the local group is small. Cosmically speaking, it's almost insignificant. It's one of the smallest galaxy groups that exists. 50 galaxies is nothing. Because just beyond the local group, things escalate in a way that makes everything we've discussed feel like a warm-up exercise. The local group is part of a larger structure called the Virgo supercluster. A supercluster is a collection of galaxy groups and galaxy clusters, all loosely connected by gravity. The Virgo supercluster contains at least 100 galaxy groups and clusters, spread across roughly 110 million light years. That's 11 times larger than the local group. The total number of galaxies in the Virgo supercluster is difficult to pin down, but it's in the range of tens of thousands, and the total number of stars across all those galaxies is estimated at around 100 trillion. 100 trillion stars. That's about 400 times more stars than the Milky Way contains, and the Virgo supercluster isn't even a particularly large supercluster. It's fairly average. There are larger ones out there, much larger. But let's stay here for a moment, because even this structure is enough to make the Milky Way seem small. The dominant feature of the Virgo supercluster is the Virgo cluster itself, a massive galaxy cluster sitting about 54 million light years from Earth. The Virgo cluster contains somewhere between 1,200 and 2,000 galaxies, many of them far larger than the Milky Way. M87, one of the most massive galaxies in the Virgo cluster, is a supergiant elliptical galaxy containing roughly 1 trillion stars. Its central supermassive black hole has a mass of about 6.5 billion times the mass of our Sun. For comparison, the black hole at the center of the Milky Way Sagittarius A star, has a mass of about 4 million solar masses. M87's black hole is more than 1,600 times heavier. In 2019, M87 became famous when the Event Horizon Telescope collaboration produced the first direct image of a black hole shadow. That image showed the silhouette of a monster so massive that our galaxy's own central black hole looks like a pebble beside it. Now, here's what I need you to understand about the Virgo supercluster. The Milky Way, inside this structure, is one galaxy among tens of thousands. If you made a map of the Virgo supercluster and each galaxy was represented by a single dot, the Milky Way would be one dot in a cloud of dots stretching across 110 million light years. You could remove our galaxy from the map entirely, and the supercluster would look essentially the same. We contribute nothing noticeable to the large-scale structure. We're background noise, but the Virgo supercluster itself is just a piece of something even larger. In 2014, a team of astronomers led by Brent Tully published a paper that redefined our understanding of cosmic structure. They discovered that the Virgo supercluster is not an independent structure at all. It's just one lobe, one small appendage, of a vastly larger supercluster they named Laniakea. The name comes from Hawaiian and means immeasurable heaven. It was chosen deliberately because the structure it describes is almost impossibly large. Laniakea spans about 520 million light years. It contains roughly 100,000 galaxies, all flowing together through space toward a common gravitational center. The Milky Way, along with everything in the local group and everything in the Virgo supercluster, is part of this flow. We're moving through space at about 370 miles per second, pulled by the combined gravity of all the mass in Laniakea. The point we're all falling toward is called the Great Attractor. The Great Attractor deserves more attention, because for decades it was one of the most tantalizing mysteries in astronomy. In the 1970s, astronomers measuring the motion of our galaxy and its neighbors noticed something they couldn't explain. The Milky Way and thousands of surrounding galaxies were all drifting in a particular direction at roughly 600 kilometers per second. That's over 1 million miles per hour. This motion was separate from the general expansion of the universe. Something was pulling us. Something massive. But when astronomers looked in that direction, toward the constellations Norma and Triangulum Australe, they couldn't see anything obvious. The problem was that the Great Attractor lies directly behind the thickest part of the Milky Way's disk, hidden behind dense clouds of gas, dust, and billions of foreground stars. It's like trying to see a bonfire on the horizon through a dense fog. The light is there, but you can't get a clear view. It took decades of work, using X-ray telescopes, infrared telescopes, and radio telescopes that can peer through the dust, for astronomers to piece together what was hiding back there. What they found was not a single object, but an enormous concentration of galaxy clusters centered on the Norma cluster. This region contains an immense amount of mass, both visible galaxies and invisible dark matter, enough to gravitationally influence 100,000 galaxies across hundreds of millions of light years. But even the Great Attractor wasn't the end of the story. It's being pulled by something even more massive behind it. The Shapley supercluster, about 650 million light years away, contains thousands of galaxies with a combined mass estimated at around 10,000 trillion times the mass of our Sun. Its gravitational influence reaches across hundreds of millions of light years, pulling Laniakea and everything in it like a current in an invisible ocean. Each time we think we've found the thing doing the pulling, we discover it too is being pulled by something bigger and farther away. It's gravitational nesting dolls all the way out to the edges of what we can observe. Let me try to give you a sense of Laniakea's scale. If you shrunk it down so that the Milky Way was the size of a single grain of sand, Laniakea would be about the size of a large room. Our entire galaxy, with its hundreds of billions of stars and its 100,000 light-year diameter, would be one grain of sand in a room containing 100,000 other grains. And the room wouldn't be packed with sand. The grains would be scattered sparsely, separated by distances that, even in this shrunken model, would be measured in feet. The room would be mostly empty. The grains of sand would be lonely specks floating in vast amounts of nothing. And Laniakea, enormous as it is just one supercluster among many. The universe contains millions of superclusters, each one comparable in size to Laniakea or larger, each one containing tens of thousands or hundreds of thousands of galaxies, each one separated from the others by even vaster stretches of empty space. Let's talk about that empty space, because the emptiness of the universe is just as important as the fullness when it comes to understanding scale. Between superclusters lie cosmic voids. These are regions of space where almost nothing exists. No galaxies, no stars, no planets, just darkness and near vacuum stretching across hundreds of millions of light years. The largest known void is the KBC void. It's roughly 2 billion light years across. 2 billion light years of almost nothing. If you were transported to its center and looked out in every direction, you would see nothing. No galaxies, no stars. Just blackness stretching for 1 billion light years before you'd encounter the nearest significant concentration of matter. The loneliness would be absolute, a darkness so vast that the entire Milky Way could be dropped into it and vanish without a trace. These voids aren't rare or unusual. They're the dominant feature of the universe. Roughly 80% of the universe's volume is void, empty space. The galaxies, the clusters, the superclusters, all the matter and light and structure we've been talking about, all of it occupies only about 20% of the total volume. The universe is overwhelmingly empty. The stuff in it, the galaxies and stars and planets, is the exception, not the rule. Matter is a thin film stretched across the surface of an enormous bubble of nothing. When astronomers map the three-dimensional positions of galaxies across hundreds of millions or billions of light years, a pattern emerges. Galaxies aren't scattered randomly. They cluster along filaments, long thread-like structures stretching across the cosmos, surrounding the voids like the walls of soap bubbles. These filaments connect to each other at nodes where galaxy clusters sit. The whole structure looks like a cosmic web, an intricate three-dimensional lattice of matter and emptiness, stretching in every direction for as far as we can see. Here's an analogy that might help. Imagine a natural sponge, the kind full of irregular holes and tunnels. Now imagine you could blow that sponge up to the size of the observable universe. The solid material, the thin walls and threads between the holes, represents the filaments where galaxies live. The holes and tunnels are the cosmic voids. The solid material is thin, very thin. Most of the sponge's volume is hole, not wall. That's the cosmic web. The galaxies and clusters exist on the thin walls and threads between enormous empty cavities. And the cavities, the voids, make up the vast majority of the total volume. You live on one thread in one wall of this cosmic sponge, on one tiny grain embedded in the wall material. And the sponge stretches in every direction farther than light has travelled since the beginning of time. This cosmic web is the largest scale structure in the universe. The filaments can stretch for hundreds of millions of light years. The voids they surround can span billions. The nodes where filaments intersect contain the largest galaxy clusters, some with thousands of member galaxies. And the whole thing is held together by dark matter, an invisible substance that makes up about 27% of the universe's total energy content. We can't see dark matter. It doesn't emit light. It doesn't absorb light. It doesn't interact with light at all. But it has gravity. And that gravity is what shapes the cosmic web. What pulls galaxies into filaments and clusters. What holds the whole vast structure together. The visible galaxies are like dewdrops on a spider's web. The web itself, the underlying scaffolding, is made of dark matter. Within this cosmic web, astronomers have identified some truly enormous structures. The Sloan Great Wall, discovered in 2003, is a sheet of galaxies stretching about 1.37 billion light-years across. That's more than 13,000 times the diameter of the Milky Way. It contains tens of thousands of galaxies arranged in a relatively thin wall-like formation. If the Milky Way were a grain of rice, the Sloan Great Wall would be longer than 10 football fields laid end to end. But the Sloan Great Wall isn't the largest structure. The Hercules Corona Borealis Great Wall, identified in 2013 through observations of gamma-ray bursts, is estimated to span roughly 10 billion light-years. 10 billion light-years. That is 100 million times the diameter of the Milky Way. Light travelling at the maximum possible speed would need 10 billion years to cross this single structure. That's more than 70% of the age of the entire universe. The existence of a structure this large actually challenges our cosmological models, because according to our understanding of how gravity assembles matter over time, there shouldn't have been enough time since the Big Bang for something this large to form. The universe is only 13.8 billion years old. Gravity works gradually, pulling matter together slowly over cosmic time. Structures spanning 10 billion light years shouldn't be possible yet, and yet, there it is. Either our models are incomplete or the universe is stranger than we thought. These filaments and walls and voids form the cosmic web, and the cosmic web fills the observable universe. So let's talk about what the observable universe actually is, because this is where the final layer of scale reveals itself, and everything we've discussed so far gets reduced to a rounding error. The observable universe is the region of space from which light has had time to reach us since the Big Bang. The universe is 13.8 billion years old. Light travels at a finite speed, so there's a maximum distance from which light can have traveled to reach us, a cosmic horizon beyond which we cannot see. You might expect that this horizon would be 13.8 billion light years away. After all, if the universe is 13.8 billion years old, and light has been traveling toward us for that entire time, shouldn't the most distant visible objects be 13.8 billion light years away? They should, except for one critical detail. The universe has been expanding the entire time. Space itself is stretching. Not the objects in space moving through space, but space itself growing, creating more distance between objects. This expansion has been happening since the Big Bang, And it means that a galaxy whose light has been traveling toward us for 13 billion years is now much farther away than 13 billion light years. During the 13 billion years that light was traveling toward us, the space between us and that galaxy was expanding, stretching, growing. By the time the light arrives, the galaxy has been carried much farther away by the expansion of space. The result is that the observable universe has a radius of about 46.5 billion light years, making it roughly 93 billion light years across. 93 billion light years. Let me try to make you feel this number, even though I know it's impossible. The Milky Way is 100,000 light years across. The observable universe is 93 billion light years across. That means you could line up 930,000 Milky Way galaxies side by side, and they would just barely span the diameter of the observable universe. 930,000 copies of a galaxy that already contains hundreds of billions of stars, each one separated from the next by trillions of miles of empty space. That's how wide the observable universe is. Within this volume, astronomers estimate there are approximately 2 trillion galaxies. 2 trillion. That's 2 million million. Each galaxy contains anywhere from a few million stars to several trillion stars, depending on its size. The total number of stars in the observable universe is estimated at roughly 200 billion trillion. Written as a number, that's a 2 followed by 23 zeros. If each star were a grain of sand, you would need enough sand to fill several 100,000 Olympic-sized swimming pools. And each of those grains represents a real star, a nuclear furnace potentially surrounded by planets, separated from its nearest neighbor by light years of emptiness. And we know from decades of exoplanet research that most stars have planets. The Kepler Space Telescope and other instruments have shown us that planetary systems are not rare. They're the norm. Most stars have at least one planet, and many have several. If even a fraction of those planets are rocky and in the habitable zone of their star, the number of potentially Earth-like worlds in the observable universe is staggering. Estimates vary, but there could be billions of habitable zone rocky planets in the Milky Way alone. Across 2 trillion galaxies, the total number could be in the quintillions. Numbers so large they cease to mean anything to a human mind. Now I want you to try something. Try to imagine the observable universe. Try to picture a sphere 93 billion light years across, filled with 2 trillion galaxies, each containing billions or trillions of stars, each star potentially surrounded by planets, all of it woven into a cosmic web of filaments and voids. Try to hold that image in your mind. You can't. I know you can't. I can't either. No human being can. Our brains simply don't have the architecture for it. We can understand it mathematically. We can write equations that describe it. We can build computer simulations that model it, but we cannot picture it. We cannot feel it the way we feel the distance to the grocery store or the size of our living room. The observable universe exists at a scale so far beyond human intuition that attempting to visualize it is like asking an ant to picture the Pacific Ocean. The ant can stand on the shore and sense that something large is in front of it, but it cannot grasp what it is looking at. Its brain isn't built for that scale. Neither is yours. Neither is mine. And here is the part that genuinely disturbs me. The observable universe, as unimaginably vast as it is almost certainly not the whole universe. It's just the part we can see. Beyond the observable horizon, beyond the 46.5 billion light-year radius from which light has had time to reach us, there is almost certainly more universe, More galaxies, more stars, more planets, more voids, more filaments, more of everything, stretching outward in every direction, beyond the reach of our telescopes, beyond the reach of light itself, given the time that's elapsed since the Big Bang. How much more? We don't know. Nobody knows. It could be that the universe is a few times larger than the observable part. Some models of cosmic inflation, the rapid expansion that occurred in the first tiny fraction of a second after the Big Bang, suggests that the total universe could be enormously larger. Some estimates suggest the total universe might be at least 250 times larger in diameter than the observable universe. Others suggest it could be 10 to the power of 23 times larger. A number so absurdly vast that even writing it down feels like a meaningless exercise. Some models suggest the universe might be infinite, stretching on forever in every direction, with no edge, no boundary, no end. If the universe is infinite, then the observable universe, this 93 billion light-year sphere containing 2 trillion galaxies and 200 billion trillion stars, is literally nothing. 0% of infinity is 0. The entire observable universe, everything we've ever seen, everything we will ever see, everything any telescope could ever detect from our position in space, would be an infinitely small fraction of the total. It would be like scooping a thimble of water from an ocean that has no shores and claiming you'd sampled the sea. And within that thimble, the Milky Way would be 1 grain of salt dissolved in the water, and Earth would be a single atom within that grain, and you would be a subatomic particle within that atom. The metaphor doesn't even work because at these scales, every metaphor collapses. There is nothing in human experience that maps onto the relationship between you and an infinite universe. The size difference is not large. It is not enormous. It is not immeasurable. It is, in the most precise mathematical sense, undefined. You are a finite thing trying to comprehend an infinite thing, and the tools of comprehension simply don't extend that far. But let's come back to what we can observe, because even within the observable universe, there's a feature of cosmic structure that makes the emptiness feel even more overwhelming. I mentioned the cosmic voids earlier. Those enormous regions of near nothingness between the filaments of the cosmic web. But I want to revisit them, because they reveal something about the universe that most people never consider. The universe isn't just big, it's mostly nothing. It is overwhelmingly, crushingly empty. Consider this. If you removed all the stars in the observable universe and distributed the remaining matter, the gas, the dust, the dark matter, the planets, everything, evenly throughout the entire volume of the observable universe, the average density would be roughly 5 atoms per cubic meter. 5 atoms. In a space the size of a large closet. That's how empty the universe is on average. The space between galaxies is so devoid of matter that it makes the best vacuum we can create in a laboratory look positively crowded. A laboratory vacuum might contain a few trillion molecules per cubic meter. Intergalactic space contains a handful of atoms. The difference is a factor of roughly 1 trillion. Intergalactic space is 1 trillion times emptier than the best vacuum on Earth. And this emptiness isn't just a feature of the space between galaxies. Even inside galaxies, even inside the Milky Way, space is overwhelmingly empty. The average distance between stars in our region of the galaxy is about 4 to 5 light years. If you randomly selected a cubic light year of space within the Milky Way, the chances of that cube containing even a single star are extremely small. You'd almost certainly get nothing but vacuum, a cube of emptiness 24 trillion miles on a side with nothing inside it. The universe is a place where matter is the exception and emptiness is the rule. The galaxies, the stars, the planets, the cosmic web itself, all of it is a thin, fragile lattice of matter suspended in an ocean of nothing that dwarfs it by every possible measure. We look up at the night sky and see stars and think the universe is full. But the stars are a trick of perspective. They're the only things emitting light. So they're the only things we see. The darkness between them, which makes up almost all of the actual volume of the universe, is invisible to us. We see the exceptions and miss the rule. This brings us to something I've been building towards since the beginning. The title of tonight's exploration is "The Universe is much bigger than you think, and it's not even close." And by now, you might think you understand what that means. You've heard the numbers. You've heard the comparisons. You know the observable universe is 93 billion light years across. You know it contains 2 trillion galaxies. You know it might be a tiny fraction of the total universe. You know about the cosmic web and the voids and the filaments. But here's the thing. Even now, even after all of that, your mental picture of the universe is still too small. I know it is, because mine is too. Every human being who has ever tried to picture the universe has produced a mental image that's too small, because the human brain cannot generate an image large enough. We can know the numbers, we can recite them, we can do the math, but the feeling, the gut level, intuitive understanding of what those numbers mean, that part never comes. It's like trying to feel the weight of a mountain by reading its mass on a piece of paper. You can know the number, but you can't feel it in your hands. The phrase "not even close" in the title doesn't refer to a comparison between 2 specific things. It refers to the gap between what you imagine and what's actually there. No matter how large you think the universe is, the real universe is larger. And the difference between your mental picture and reality isn't a small gap that better education could close. It's a chasm so wide that no amount of learning, no number of analogies, no quantity of data will ever fully bridge it. Your brain evolved to track predators on a savanna. It was never meant to hold a cosmos. And yet, knowing this, knowing that we can't truly grasp it, is itself valuable. Because it tells us something about where we are and what we're dealing with. We live in a universe that is fundamentally beyond the reach of human intuition. We can probe it with mathematics, we can photograph it with telescopes, we can model it with supercomputers, but we cannot feel it. We cannot experience it the way we experience the warmth of sunlight or the sound of rain. The universe at its true scale exists in a realm that our senses and our intuition were never designed to access. And that gap, that permanent, unbridgeable gap between what we can know and what we can feel, is going to become even more important in what comes next. Because we haven't yet talked about what lies beyond the observable universe. We haven't talked about what the expansion of space really means. And we haven't confronted the most unsettling implication of all, that there are regions of the universe that we will never see, not because our telescopes aren't powerful enough, but because the light from those regions will never reach us. Not in 1 billion years, not in 1 trillion, not ever. That's where we're going next. And when we get there, even the observable universe, this 93 billion light-year sphere that already dwarfs everything you've ever known, is going to start looking small. Everything we've talked about so far has been contained within a bubble. A very large bubble, yes. 93 billion light-years across, containing 2 trillion galaxies and 200 billion trillion stars. But a bubble nonetheless. A finite region of space defined not by any physical wall or boundary, but by a limit far more fundamental. The speed of light and the age of the universe. The observable universe is not the universe. It's the part of the universe we can see. And those are two very different things. The observable universe is bounded by a horizon. A cosmic horizon, beyond which light hasn't had time to reach us since the Big Bang 13.8 billion years ago. This horizon isn't a wall you could fly to and touch. It's not a physical barrier made of anything. It's a consequence of two simple facts. Light travels at a finite speed, and the universe has existed for a finite time. Combine those two facts and you get a maximum distance from which information can have reached us. That distance, in every direction, is about 46.5 billion light-years. Beyond that, there might be more universe. Almost certainly there is more universe. But we can't see it. We've never seen it. And depending on what happens next, we might never see it. Let me explain why the observable universe has a radius of 46.5 billion light-years instead of 13.8 billion, because this is one of the most commonly misunderstood facts in cosmology, and it gets to the heart of what makes the universe so much bigger than people think. When the universe was very young, just a few 100,000 years after the Big Bang, it was filled with a hot, dense plasma. Light couldn't travel freely through this plasma. It was like trying to see through fog. Photons would bounce off particles almost immediately after being emitted. Then, about 380,000 years after the Big Bang, the universe cooled enough for atoms to form. The fog cleared. Light was suddenly free to travel through space, and it's been traveling ever since. The oldest light we can see, called the cosmic microwave background radiation, comes from this moment. It was released 380,000 years after the Big Bang and has been traveling toward us for about 13.4 billion years. This ancient light is everywhere. It fills the entire sky, coming from every direction equally. It's not visible to your eyes because it's been stretched by the expansion of space into microwave radiation, far below what human vision can detect. But radio telescopes can see it clearly. When you tune an old analog television to a channel with no broadcast, a small fraction of the static on the screen is actually caused by the cosmic microwave background. You're watching the afterglow of the Big Bang. In 1964, two radio astronomers named Arno Penzias and Robert Wilson were working with a large antenna at Bell Labs in New Jersey. They kept detecting a faint background hiss they couldn't eliminate. They checked their equipment. They cleaned pigeon droppings off the antenna. Nothing worked. The hiss was always there, from every direction, at all times. Eventually they realized they were detecting the afterglow of the Big Bang, predicted by theory but never before observed. That discovery earned them the Nobel Prize. Since then, satellites like the Planck spacecraft have mapped the cosmic microwave background in extraordinary detail. The radiation is almost perfectly uniform, with temperature variations of only about 1 part in 100,000. These tiny variations are the seeds of everything you see in the universe today. The slightly denser regions in that primordial glow are where gravity eventually pulled matter together to form the first galaxies, the first stars, the first planets. The cosmic web grew from those minuscule fluctuations. Everything, from the largest supercluster to the smallest moon, traces its origin to those tiny hot and cold spots in the ancient glow. But during those 13.4 billion years since the cosmic microwave background was released, the universe has been expanding. Space itself has been stretching. The point in space from which that ancient light was emitted has been carried outward by the expansion of space. By the time that light reaches us today, the source from which it was emitted is now roughly 46.5 billion light years away. The light traveled for 13.4 billion years, but during that journey, the expansion of space stretched the distance between us and its origin to 46.5 billion light years. This is the key concept. Space is expanding. Not the galaxies moving through space, but space itself growing. Everywhere. In every direction. Between every object. New space is being created between everything all the time. For nearby objects, this expansion is negligible. The space between the Earth and the Moon isn't expanding in any meaningful way, because gravity overwhelms the expansion at small scales. The space within our solar system isn't expanding noticeably. The space within the Milky Way isn't expanding noticeably. Gravity holds these structures together against the expansion. But on large scales, between galaxy clusters separated by hundreds of millions or billions of light years, the expansion dominates. And the farther apart two objects are, the faster the expansion carries them away from each other, because there's more space between them and every bit of that space is expanding. This leads to something that sounds impossible, but is absolutely true. There are galaxies in the observable universe whose light we can see, but which are currently moving away from us faster than the speed of light. I need to be careful here because this sounds like a contradiction. I said earlier that nothing could travel faster than light. And that's true. Nothing can move through space faster than light. But the expansion of space isn't movement through space, it's the growth of space itself. And there's no speed limit on how fast space can expand. Two galaxies can be carried apart by expanding space at any speed, even faster than light, without violating any law of physics. Because neither galaxy is actually moving through its local space at superluminal speed. Each one is sitting relatively still in its own neighborhood. It's the space between them that's growing. Think of it this way. Imagine two ants standing on a rubber band. The ants aren't walking, they're standing still, but someone is stretching the rubber band. The ants move apart, not because they're walking, but because the surface they're standing on is expanding. If the rubber band is long enough and being stretched fast enough, the ants can separate faster than either of them could walk. Neither ant is moving faster than its maximum walking speed. The rubber band is just expanding faster than their legs could carry them. That's what's happening with the universe. Galaxies aren't flying through space at superluminal speeds. Space is expanding, carrying them apart. Now, here's where this gets truly sobering. Because the expansion of space is accelerating. In 1998, two independent teams of astronomers made one of the most shocking discoveries in the history of science. By observing distant supernovae, they found that the expansion of the universe isn't just continuing, it's speeding up. Whatever is driving the expansion is getting stronger over time. We call this force dark energy, which is an honest name because it's dark in the sense that we can't see it, and it's energy in the sense that it has real physical effects on the universe. But beyond that, we don't know what it is. Dark energy makes up about 68% of the total energy content of the universe. It's the dominant component, and it's pushing space apart at an ever-increasing rate. Think about what that means. More than 2/3 of everything the universe contains, in terms of energy, is something we cannot see, cannot touch, and cannot explain. We know it's there because we can measure its effect. The expansion is accelerating. Something is causing that acceleration. We call it dark energy. But if you ask a physicist what dark energy actually is, the honest answer is we don't know. It might be a property of space itself. It might be a new force field. It might be something our current theories aren't equipped to describe. It is one of the deepest unsolved mysteries in all of science. And yet its effects are shaping the fate of the entire universe. The consequences of accelerating expansion are staggering and deeply unsettling. Because of this acceleration, there are galaxies that we can currently see, galaxies whose light has already reached us and been recorded by our telescopes, that we will never be able to reach. Even traveling at the speed of light, we could never get to them, because the space between us and them is expanding faster than light can cross it. They're receding from us superluminally, carried by the expansion of space. And the expansion is accelerating, which means they're receding faster and faster. Every second, the gulf between us and those galaxies grows wider. Every second, more space is created between us and them. They are, in the most absolute physical sense, beyond our reach. Forever. But it gets worse. Not only can we never reach those galaxies, we're going to lose sight of them. The light they're emitting right now, at this very moment, will never reach us. It can't. The space between us and them is expanding too fast. The light is trying to cross the gap, moving at 300,000 kilometers per second. But the gap is growing faster than the light can traverse it. That light will travel forever and never arrive. It will be like a swimmer trying to reach a shore that's receding faster than they can swim. They'll swim until they can't swim anymore, and the shore will still be pulling away. This means the observable universe is shrinking. Not in actual size, but in terms of what new information can reach us. Galaxies that are currently right at the edge of our cosmic horizon are, one by one, being carried beyond it by the expansion of space. Their light is being redshifted, stretched to longer and longer wavelengths, becoming fainter and fainter, until eventually it fades beyond the ability of any telescope to detect. Over billions of years, galaxy after galaxy will slip past our cosmic horizon and vanish from our view. Not destroyed. Still there. Still full of stars and planets, and possibly life. But invisible to us forever. Carried into a darkness from which no signal can return. If you could fast forward the cosmic clock far enough, billions of years into the future, the night sky would be very different from what we see today. Almost all the galaxies visible today would be gone, pushed beyond the observable horizon by the relentless expansion of space. The local group, our small collection of about 50 galaxies, would have merged into a single, large elliptical galaxy, and that galaxy would be alone, floating in an apparently empty universe with no other galaxies visible in any direction. Future astronomers living in that era, if there are any, would look out at the sky and see nothing beyond their own galaxy. They would have no way of knowing that trillions of other galaxies existed. No evidence of the cosmic web. No evidence of the Big Bang's afterglow, because the cosmic microwave background radiation would have been redshifted to wavelengths too long to detect. They would live in a universe that appeared to contain one galaxy and nothing else. And they would have no reason to suspect otherwise. This is not speculation. This is the straightforward consequence of accelerating expansion. as described by our best cosmological models. The universe of the far future will be a lonely place. The richness and variety we see today, the 2 trillion galaxies, the cosmic web, the filaments and voids, all of it will be invisible to future observers. The evidence will have been erased, not by some catastrophe, but by the quiet, relentless stretching of space. We happen to live at a moment in cosmic history when the universe is still young enough, still compact enough, that we can see the evidence of its origin and its vast structure. That window will not stay open forever. In a sense, we are lucky. We exist at one of the only times in the universe's history when it is even possible to figure out what the universe is, and the far, far future is even more desolate. As trillions of years pass, the stars themselves will begin to die. The universe will slowly run out of the hydrogen gas needed to form new stars. Star formation will decline, sputter, and eventually cease. The last stars to burn will be the red dwarfs, tiny, dim, miserly stars that hoard their fuel and burn for trillions of years. But eventually, even they will exhaust their hydrogen and fade. The universe will enter an era of darkness. No new stars, no sunlight on any world. The only objects left will be stellar corpses. White dwarfs cooling slowly toward absolute zero. Neutron stars spinning down to silence. Black holes drifting through the emptiness. Slowly evaporating over timescales so long that the current age of the universe would be less than a single tick of the clock by comparison. The most massive black holes in the universe, those billions of times the mass of our sun, sitting at the heart of the largest galaxies, would take roughly 10 to the power of 100 years to fully evaporate through Hawking radiation. That's a 1 followed by 100 zeros. The current age of the universe, 13.8 billion years, is a 1 followed by 10 digits. The difference between 10 digits and 100 digits is not a difference of degree, it's a difference of kind. It's a number so large that the word large has no business being anywhere near it. And after even the black holes are gone, the universe will be a thin, cold soup of elementary particles, spread across distances so vast that no 2 particles will ever interact again. No structure, no complexity, no change. Just an eternal, featureless, expanding void, getting colder and emptier forever. This is called the heat death of the universe, and it is, as far as our current physics can tell, the ultimate fate of everything. Every galaxy, every star, every planet, every atom, every thought that was ever thought, all of it ends in a whisper of fading radiation scattered across an infinity of empty space. Now, let's confront the biggest question. How large is the actual universe? Not the observable part, but the whole thing. The honest answer is we don't know. We might never know. But we have some ideas, and those ideas are enough to make the observable universe feel small. Our best models of cosmic inflation, the rapid expansion that occurred in the first fraction of a second after the Big Bang, suggests that the total universe is vastly larger than the observable part. During inflation, the universe expanded exponentially, doubling in size over and over again in an incomprehensibly short time. Different models of inflation produce different estimates for the total size of the universe, but most of them agree on one thing. The observable universe is a tiny, tiny fraction of the whole. Some estimates, based on measurements of the cosmic microwave background radiation by satellites like the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft, suggest that if the universe has any curvature at all, it's so slight that the total universe must be at least 250 times larger in diameter than the observable universe. That would make it at least 23 trillion light years across. But that's a lower bound based on the limits of our measurements. The actual size could be much, much larger. Some inflationary models suggest the total universe could be 10 to the power of 23 times larger than the observable universe. That's a 1 followed by 23 zeros. If the observable universe were the size of a single atom, the total universe at this scale would be larger than the observable universe itself. Let that sink in. The observable universe, reduced to the size of an atom, sitting inside a total universe that is itself the size of the observable universe. The nesting of scales is so extreme that language itself breaks down. And some models suggest the universe might be genuinely infinite. Not very large, not unimaginably large. Infinite. Stretching on forever in every direction with no edge, no boundary, no center, no end. Just space and matter and energy going on and on without limit. If the universe is infinite, then the observable universe is infinitely small in comparison. The 93 billion light-year sphere that contains everything we've ever seen, everything any civilization anywhere in the observable universe has ever seen or will ever see, is 0% of the total. Mathematically, rigorously, absolutely 0%. An infinitely small island of visibility in an infinite ocean of darkness. If the universe is infinite, it also means something that sounds like science fiction, but is a logical consequence of probability in infinite space. If space goes on forever and matter is distributed throughout it, then every possible arrangement of matter that could exist does exist somewhere. Every possible configuration of atoms, every possible planet, every possible galaxy, every possible version of events, all of it is playing out somewhere in the infinite expanse. There would be another region of space, impossibly far away, where atoms have arranged themselves into an exact copy of the Milky Way, with an exact copy of the solar system, with an exact copy of Earth, with an exact copy of you, hearing these exact words at this exact moment, not metaphorically, literally. The distances involved would be unimaginably vast. So vast that even the word unimaginable fails to capture it. But in an infinite universe, distance doesn't matter. Everything that can happen does happen somewhere. This is not mysticism. This is mathematics. In an infinite space with a finite number of possible arrangements of matter within any given volume, the arrangements must eventually repeat. It's the same logic that says if you shuffle a deck of cards enough times, you'll eventually get the same order twice. Except, instead of 52 cards, you're shuffling the atoms of the observable universe. And instead of shuffling a few times, you have infinite space in which every possible arrangement occurs. Whether this is actually the case depends on whether the universe is truly infinite, which we don't know for certain. But the fact that it's even a possibility, that serious physicists consider it a plausible consequence of our best cosmological models, tells you something about the scale we're dealing with. We've gone so far beyond the familiar that the conversation has shifted from how big is it to is it infinite, and if so, what does that even mean? Let's bring this back to where we started. To you, to Earth, to the human brain trying to make sense of all this. You evolved on a planet that's about 8,000 miles across, orbiting a star about 93 million miles away, in a galaxy 100,000 light years wide, inside an observable universe 93 billion light years across, which is itself potentially an infinitely small fraction of a total universe that might extend forever. And that entire universe infinite or not, is slowly dying. The stars are burning out. The galaxies are drifting apart. The cosmic microwave background is fading. The evidence of everything that ever existed is being erased by the expansion of space and the passage of time. At every single step of that chain, from Earth to the solar system, from the solar system to the galaxy, from the galaxy to the observable universe, from the observable universe to the total universe, your intuition failed. It failed at 93 million miles to the sun. It failed at 4 light years to the nearest star. It failed at 100,000 light years across the galaxy. It failed at 93 billion light years across the observable universe. And it fails most completely at the idea that even the observable universe might be an infinitely small portion of what actually exists. Your brain was built to judge the distance to a predator on a savanna. It can do that brilliantly. It can gauge 20 feet or 50 feet or 100 yards with remarkable accuracy. But ask it to hold 93 billion light years, and it simply shuts down. It gives you the word big and moves on, because it has nothing else to offer. And that's the real meaning behind not even close. The title isn't saying the universe is bigger than some specific estimate. It's saying that the gap between human intuition and cosmic reality is itself larger than anything human intuition can process. You can't even correctly estimate how wrong your estimate is. The error in your mental model of the universe is bigger than any mental model you're capable of building. It's failure all the way down. But here's what I find extraordinary. You know this. You can understand, intellectually, if not intuitively, that the universe is beyond your capacity to picture. You can hold that knowledge in your mind and examine it. You can recognize the limits of your own cognition and reason about what lies beyond those limits. That's something no other known species on Earth can do. A chimpanzee can't contemplate the size of the galaxy. A dolphin can't reason about cosmic expansion. An ant can't ponder the implications of an infinite universe. But you can. You can't picture it, but you can think about it. You can do the math. You can build the telescopes. You can write the equations. You can push the boundary of understanding outward, even as the boundary of intuition stays fixed. That is what humans do. We are the species that reaches beyond what it can grasp. Every telescope we build is an admission that our eyes aren't good enough. Every equation we derive is an admission that our intuition isn't reliable. Every satellite we launch is an acknowledgement that we need tools to see what our bodies cannot. And through those tools, through mathematics and observation and relentless curiosity, we have assembled a picture of a universe so vast that it reduces everything we know to less than a rounding error. We live on a tiny planet orbiting an ordinary star in the suburbs of a fairly large galaxy that is one of 2 trillion galaxies in an observable universe that is 93 billion light years across, and probably an infinitesimally small fraction of whatever the total universe actually is. Every number in that sentence is real. Every number is based on careful measurement and observation. And every number is too large for the human brain to truly feel. The universe doesn't care about our cognitive limitations. It isn't big because we think it's big or small because we think it's small. It simply is what it is. It extends as far as it extends. It contains what it contains. And it does all of this with a complete, absolute, almost terrifying indifference to whether anyone understands it or not. The galaxies will continue drifting apart whether or not there's a mind anywhere in the cosmos trying to measure the distance between them. The cosmic web will continue its slow evolution, whether or not anyone maps it. The expansion will continue accelerating whether or not anyone writes an equation to describe it. And yet, here we are. On one small planet, inside one galaxy, within one observable bubble, a species that figured it out. Not completely, not intuitively, but enough to know what we're looking at and enough to know how much we can't see. There's a profound humility in that, and also a profound pride. Humility because we are so small that the word small doesn't begin to capture it. Pride because we are so capable that from this tiny vantage point, we've mapped structures billions of light years across. We've detected the afterglow of the Big Bang. We've measured the rate at which the universe is expanding. We've counted galaxies and weighed black holes and catalogued the chemical composition of stars that are hundreds of light years away. We did all of this from one planet, orbiting one star, using brains that evolved to track predators on grasslands. And we did it at exactly the right time. A few billion years earlier, there wouldn't have been a planet to stand on. A few trillion years later, there won't be any evidence left to find. The cosmic microwave background will have faded beyond detection. The distant galaxies will have vanished past the horizon. The universe will appear empty and cold and eternal, offering no clues about its fiery origin or its vast hidden structure. We exist in a window, a brief cosmic window when the universe is old enough to have produced beings capable of inquiry and young enough to still have evidence worth inquiring about. That window will close, and when it does, the truths we've uncovered tonight, truths about 2 trillion galaxies and a cosmic web, and an expanding universe and the fading afterglow of creation, those truths will become unfindable. Not wrong, just invisible, buried behind a horizon of expanding space that no future civilization will ever be able to peer past. So the next time someone tells you the universe is big, you can smile politely, because you know something they probably don't. You know that the word big is doing more heavy lifting in that sentence than any word has ever been asked to do. You know that even after hearing everything I've shared tonight, your mental picture of the universe is still too small. You know that the observable universe, vast as it is, might be nothing compared to what lies beyond it. You know that there are galaxies out there right now, emitting light that will never reach us, existing in regions of space we will never see, separated from us by an expansion we can never outrun. And you know that despite all of this, despite the incomprehensible vastness, despite the permanent limits of human intuition, despite the loneliness of a species trapped on one small world, in one small corner of one small galaxy, we looked up. We asked questions, we built instruments, we did the math, and we learned the truth, or at least as much of the truth as a brain built for savannas can hold. The universe is much bigger than you think, and it's not even close. That was true before you heard this. It's true now. And it will still be true tomorrow, no matter how many times you try to imagine it. The gap between your imagination and reality will never fully close. But the fact that you know the gap is there, the fact that you can think about a universe you can't picture, the fact that you're sitting on a pale blue dot wondering about things 93 billion light years away, that is the most remarkable thing I know. Not the size of the universe, but the fact that something in the universe is small enough to live on a planet and curious enough to measure everything else. That's you. A tiny, temporary, astonishing arrangement of atoms that figured out how big the room is, even though the room turns out to be bigger than anything that arrangement of atoms was ever designed to comprehend. The universe is much bigger than you think. It always will be. And somehow that's beautiful. Thank you for taking this journey with me tonight. If you found it valuable, a like or subscribe means more than you know. It helps me keep making these explorations of the cosmos. And the next time you step outside on a clear night and look up at the stars, remember what you've learned. Those points of light are all inside our galaxy. And our galaxy is one island of light in an ocean so vast that the ocean itself might go on forever. You can't see the ocean, you'll never see the ocean, but you know it's there. And knowing that changes everything, even if you can't quite say how. Sleep well tonight under the stars. And remember, they're much farther away than you think. And it's not even close. Good night.